As we have mentioned in the previous slide, shared memory is one option to do inter-process communication. It will define an area of a memory that can be shared among processes that want to communicate with each other. Do you still remember the buffer array we defined in the previous example? The buffer array is the shared memory for both producer and consumer. And also, actually, the communication is under control of user processes instead of operating system. Because we did not explicitly invoke any system call to manipulate the communication among processes. We just maintain two pointers, in and out, to know that whether the buffer is empty or not. So that the producer can put new items on the buffer and the consumer can remove the items from the buffer. Then some students may ask that, okay, Dr. Wang, the shared memory seems like very simple. So why you said the shared memory is difficult to deal with? So surely the aforementioned example is simple, but in real world may not be only have a single producer and a single consumer. It is very possible that multiple producers and multiple consumers can access the shared memory at the same time. So in that situation, you need to provide a mechanism to synchronize user process actions when they access the shared memory concurrently, right? So you can imagine if only one atom left on the buffer, however, two consumers try to access the buffer and grab the atom at the same time. If the shared memory cannot be maintained cooperatively, so when these two consumers access the buffer simultaneously, an extra copy of the last atom will be created accidentally, right? So surely the problem will happen. And on the other hand, if the buffer is almost full, such as only one buffer slot is left, then two producers try to put the new items on the buffer, then one item will be lost or overwritten by the other item. So in order to handle that multiple processes access the shared memory concurrently, so we need the help of synchronization, which will be discussed in Chapter 5. On the other hand, the other option of inter-process communication is a message passing, so which inherently include a mechanism for processes to communicate and synchronize with each other. So basically, here everything is handled by the operating system. The users do not need to worry about them anymore. So inside the message system, processes communicate with each other without using shared variables or shared memory. So in message passing, nothing is shared among processes. So that is why we do not need to use a synchronization mechanism in message passing approach. So this message passing approach provides two operations. One is called send. When one process has some data ready to be sent out to other process, it can call send function to send out the data. The other generic operation is a receive. So when a process wants to get some data from other processes, it can call receive function to receive data from other processes. And also the message size can be defined by the operating system either by fixed size or variable size, which is decided by the process. In message passing approach, when process P and Q wants to communicate with each other, they need to establish a communication link between them. So when the communication link has been established, so they can communicate with each other over the communication link and also exchange the messages with each other through using the send and the receive operations. The implementation of a communication link can be quite complicated, which needs to consider a number of things. For example, whether the link is a direct link or indirect link. So whether the link needs to be synchronous or asynchronous. and also whether the link should automatically handle its size or explicitly buffering certain size of data there. So all this stuff need to be considered. Next, we are going to talk about those issues one by one. First, let's see the direct communication. When processes use a direct communication link to communicate with each other, processes must name each other explicitly. From the previous example, when process Q wants to send a message to process P, Q needs to explicitly add P's ID into the send operation, like send P message, which means send a message to process P. On the other hand, so when P wants to receive a message from Q, it also needs to add a Q's ID into the receive operation as a receive Q message, so which means receive a message from process Q. Then let's see the property of a communication link. So when processes wants to communicate with each other, fortunately, links are established automatically by the operating system. As long as you call those operations, the operating system will help you to create a link. And also, a link is associated with exactly one pair of communicating processes. So for example, between process P and process Q, we have exactly one pair of link for them to communicate, to send and receive messages with each other. Between each pair of processes, there exists exactly one link. So no more link for one pair of processes if they already have one. So they cannot have the second link. And usually those links should be bidirectional, so which means both sides of processes, they can send and receive message from each other. In the previous example, not only P can send and receive messages to Q, but also Q can send and receive messages to P. So surely the link can be unidirectional. That means only one side of a process can send and receive the message to the other side. However, the direct communication is not perfect. So one disadvantage of a direct communication is explicitly adding the ID into the operations. So for example, when process wants to send or receive message to or from the other process, it needs to explicitly hard code the other process's ID into the operation. So how about the other process change its ID? For example, we temporarily turn off the other process and then later we restart the other process again. So the ID of that process will be changed. So in that situation, the process cannot send or receive message to the newly started process through the hard-code old ID. The old hard-code ID parameter must be changed to dynamically ID parameters, right? So which introduce extra difficulty for us to handle. So that's the one disadvantage for this direct communication approach. In indirect communication, messages are directed and received from mailboxes instead of a process itself. The mailboxes also referred to as ports. So each mailbox or port has a unique number or ID. So when two processes want to communicate with each other, so if and only if they share a mailbox or a port. So the properties of this kind of a communication link are listed as follows. A link can be established if and only if processes share a common mailbox. A link may be associated with many processes if those processes they share the same mailbox. And also, each pair of processes may share several links because each pair of processes may share several mailboxes. And also, the link may be unidirectional or bidirectional. In indirect communication, we have three operations. So when processes they want to communicate with each other, we must create a new mailbox for them. And then processes can send and receive messages through this mailbox. When the communication is done, the mailbox needs to be destroyed. Here is the primitives are defined as follows. So we still have a send and receive operations. So instead of adding the process ID into the operation, we add a mailbox ID as a parameter into the operations. Then the message will be sent or received to or from mailbox instead of processes directly. For example, we have two processes, P and Q. So they want to communicate with each other, and then the operating system will create a mailbox A for them, so that P and Q they can exchange the messages through mailbox A. And later, P and Q they want to communicate with process R. Then R can join in mailbox A as well. And later, process Q and R, they want to communicate with another process, which is S. And then the operating system will create another mailbox, which is a mailbox B. And then the process QRS, they can communicate with each other through mailbox B. It's something like this. And then QRS, they can communicate with each other. So here you can see that between Q and R, we have multiple links there, and each link associated with a different mailbox. And for each mailbox, A and B, each one can associate with multiple processes. When we talk about message passing, we have mentioned that the synchronization is handled by operating system. The users they do not need to worry about how the synchronizations get implemented. However, we still need to know how the synchronization works so that we can handle those operations correctly. When we want to use a message passing to send and receive messages between two processes. For example, here we have a blocking, which is considered synchronous. So when a process called the blocking send operation, the process will be blocked or stuck until the data is delivered. Correspondingly, when the blocking receive operation has been called by a process, the process will be blocked until the data is received by this process. On the other hand, the non-blocking is considered asynchronous. So when a process calls non-blocking send operation, no matter the data is delivered or not, the process will return immediately. Similarly, when a non-blocking receive is called, so no matter the data is received or not, the process will return immediately. So later you will know that. So actually we use other system call to check the status, so whether the data has been delivered or not. In real world, when you use a message passing approach, different combinations of blocking and non-blocking operations are possible. So we may have a blocking send with a non-blocking receive, and also non-blocking send with a blocking receive. But the most common combination is blocking send with a blocking receive. So since both send and receive operations are blocked before the data arrives, so it's just like a rendezvous. Therefore, we call it rendezvous. With the rendezvous approach, the example we previously talked about, that producer-consumer becomes trivial. Down below shows you the pseudocode of producer and consumer example. Compared to the shared memory version, so this one is much more simpler. Within the producer, so when a new item has been produced, it will call the blocking send operation to send the new item to customer. On the other hand, the consumer will call the blocking receive operation to wait the new item arrive. Before the new item received by the consumer, the producer process will be blocked. Until the new item is received by the consumer, the producer process will be returned. So similarly, the consumer will be blocked until the new item has been received, and the consumer process will be returned as well. When two processes want to communicate with each other over a link, there may be multiple messages exchanged over the link. If the process who receives the messages cannot deal with those messages on time, the messages will be temporarily buffered so that the receiver can eventually deal with those messages. Actually, there are three ways to implement the buffer. The first one is zero capacity, which means there's no buffer at all. So after the sender calls the send operation, the sender will be blocked until the message received by the receiver. The second one is a bounded capacity. The sender can continually send the message to the receiver until the buffer is almost full. For this way, the buffer is with limited capacity. So actually, the buffer size is fixed. If the receiver cannot retrieve the message as quick as the sending speed, so eventually the buffer will be filled up and the sender will be blocked until the new space is available on the buffer. For the last one, unbounded capacity, the sender can send whatever numbers of messages to the other side. However, you know that in real world, there's no unlimited hardware. So usually we treat the extreme large buffer as an unbounded capacity. But for some abnormal situation, the buffer can still be filled up.